Today it is the third lecture of the foundational course on group theory. Will be taken by Pratichi Paramita of B.Math second year. So over to you, Pratichi.
Good
Please
evening,
share the
everyone.
screen.
Yeah, yeah. Is it visible now?
Yeah, now it is visible.
Okay. So, good evening, everyone. My name is Pratichi Paramita. I'm from B.Math second year, and basically, I plan to cover quotient groups, normal subgroups, a few examples of groups, and the isomorphism theorems. And before I begin, I actually would like to ask if everyone is comfortable with the idea of cosets, because quotient groups are going to be on cosets. So, does anybody have any problem in the understanding or anything in cosets? Yeah, okay. If there is no problem, then I'll begin with.
Can you recap it a bit before going
Okay.
to? Yeah,
Yeah.
thank you.
Mm. So, basically, cosets we define. So, suppose H is a subgroup of G, and then we define left cosets of H as if A is an element of G, then AH is a left coset of H in G. And I hope you remember the equivalence relations. A is congruent to B mod H, and it is an equivalence relation. And once we prove that it is an equivalence relation, we can say that these equivalence classes are going to partition G. That is, they are going to so any two equivalence classes, distinct equivalent classes, will have no elements in common. So they're going to partition G. So basically, what I'm saying is that if AH and BH are two distinct equivalence classes, two distinct left cosets of H and G, then there are no elements common in AH and BH. Is that fine?
Yeah,
Yeah. So left coset, how I will define left coset is that if H is a subgroup of G and A is an element in G, then AH is a set of all elements AH where H lies in capital H. This is a left coset. There is nothing special about a left coset. We can have right cosets also. So just like a right coset will be HA, which is HA, H and H. So just like left cosets are partitioning G, right cosets will also partition G. So I begin with talking about index of a coset. So index of a subgroup H and G, say H is a subgroup of G, then index of H in G is the number of left cosets of H in G. If G is finite, that is the cardinality of G is finite, then we can say that, and this index is denoted as this, and if G, the cardinality of G, that is the number of elements in G is finite, then this is nothing but order of G upon order of H. This is the number of elements in G, order of G is the number of elements in G, and order of H is the number of elements in H. And this is, and if it's infinite, then you simply say that it is the number of left cosets, or equivalently the number of right cosets of H and G. So before I move ahead, I'll just ask a simple question. If I have an infinite group, can I have a subgroup which has finite index? Anybody? Basically, I'm asking
Yes,
that
I
if
think.
yeah, can you give me an example?
Take the G as the group of all non-zero real numbers and the subgroup as the all positive real numbers.
G as all the non-zero real numbers and
Under multiplication, both.
under multiplication, and subgroup is positive.
Yes.
Okay. Yeah. Yes, that would work. So basically, what I'm saying is that if I have an infinite, if I have a group which has infinite number of elements, then I can have a subgroup which has finite index. So again, this was a very trivial example. I have another trivial example, say the set of integers, and I'll take the set of even integers. So that is just about cosets. So I'm going to talk about something called quotient groups. Quotient groups are nothing but I have a subgroup H and G, and I know that the set of left cosets of H and G are partitioning G. So I have a set of left cosets of H and G. Is that set a group? Is my question. Is that set going to be a group? So I'll say that if the set of left cosets equivalently, if we are dealing with right cosets, it could have been right cosets, but since we talk about left cosets, we are going to just use left cosets. But if the set of left cosets form a group, then it is called a quotient group. And we denote it as G mod H. So that is just the definition, but then now I'll ask, when is it going to form a group? So from the first session only, does anybody remember the properties of a group?
The
Yes.
defining property.
Yeah.
Yeah, the operation should be associative. There should be an identity element, and there should be inverses of every element.
Is that all?
And closure.
And closure, yeah, right. So we'll consider closure right now. So I am going to take a group N, and I am specifically denoting, I'm going a subgroup N. I'm specifically denoting it as N, and I will mention why. I'm going to take a subgroup N of G, and I am saying that G mod N is going to form a group. That is, G mod N is a quotient group. Quotient groups are also known as factor groups. So I'm going to say that G mod N is a group. Then G mod N should satisfy closure. That is, if suppose G1N and G2N are two left cosets of N in G, that is, they belong to G mod N, then G1N, G2N should also be a left coset of N in G. So if it is a left coset, that means there is some element G3 and N. So this has to be of this form. So G1 and G2N has to be of the form G3N. So if it satisfies closure, then I'm one more step closer to say that it is a quotient group. G mod N is a quotient group. I am proving G mod N is a quotient group. So my claim is that G mod N is a quotient group. That means if G1N and G2N are in G mod N, then G1 and G2N should also be a left coset. That is, it should be of the form G3N for some element G in capital G. Now, N is a subgroup of G. That means E, the identity of G, should belong to N. So this simply means that G1E belongs to G1N and G2E belongs to G2N. Then G1E, G2E belongs to G1N G2n, and this is nothing but G3n. This is nothing but G1, G2. So I'm saying that G1, G2 is in G3n. Now I know that the left cosets, the set of left cosets are going to partition G. That means G1, G2, this element that is in G, will lie in only one left coset of n in G. And that left coset can also be said as G1, G2n. Is that fine?
Yes.
It's okay.
Yeah.
Yeah. So that means I can say that G3n is nothing but G1, G2n. This does not imply that G1, G2 is G3. It is, so if this is my group G and these are my cosets, left cosets, then this may be some G3 and this may be some G1, G2. But since they belong to the same left coset, G3n is nothing but G1, G2n. So this does not mean that G1, G2 is G3. It's important. So I'll say that G1, G2 is in G1, G2n. That means G1n, G2n is nothing but G1, G2n if J mod n is a quotient group. Right. So now I'll go ahead and prove the condition required. So for all n1 in n, I have this G1n, G2n is equal to G1, G2n. So for all n1 in n, there should exist n2 and n3 in n such that G1 n1, G2 n2 is equal to G1, G2, n3. And this has to be satisfied for all G1, G2 in G. So I can say that for G mod n to be a quotient group, for all G1, G2 in G, and for all n1 in n, there exist n2 and n3 in n such that G1, n1, G2, n2 is G1, G2, n3. Then I'll multiply the inverse of G1 on the left. So G1 inverse, G1, n1, G2, n2 is nothing but G1 inverse, G2, n3. So this implies E n1 G2 n2 is E, sorry, this is G1, E G2 n3. Then this implies n1 G2 n2 is G2 n3. So n1 G2 n2 n2 inverse is G2 n3 n2 inverse. So n1 G2 is G2 n3, and this simply implies that n1 G2 n3 inverse, G2 inverse n1 G2 is equal to n3. So that means for all G2 in G,
In the previous step, wasn't there an n2 inverse after G2 n3?
yeah, I'm so sorry. This is an n2 inverse, but n3, n2 inverse, so n3 is an element of capital N and n2 was an element of capital N. N is a subgroup. So n2 inverse should also belong to capital N. And from closure, I can say that n3, n2 inverse is in N. So that means I can denote this by some element, say n4. So I'll take this as n4. Yeah, sorry. So I'll say that for all G2 in G and N1 in N, there exists some N4 in N such that G2 inverse N1 G2 is equal to N4. That simply means that G2 inverse N1 G2 belongs to capital N for all G2 in G and for all N1 in N. and n1 in n. This is my condition for closure. And this is when we are going to define something called a normal subgroup. Excuse me. So I had G2 inverse N1 G2 belongs to N. I'll just replace G2 and N1. They were arbitrary elements, so I'll just replace them by G inverse NG belongs to N. And this is the condition for a normal subgroup, something called a normal subgroup. So a normal subgroup is a subgroup N of G such that for all N in N and G in G, G inverse NG is in N. So now I'll claim the set of left cosets of N in G form a group if and only if N is a normal subgroup of G. So before I go ahead and prove my claim, I'll talk a bit about quotients. So does anybody know why the group was named quotient group? Or have any idea of why it was named quotient group? So as a starting point, maybe think about integers. When we are dividing something, when we are dividing an integer by an integer, we get something called a quotient and something called a remainder.
From modular arithmetic,
From modular arithmetic, why? Like
like
how?
so Z mod NZ would look like the remainders we get mod N.
Hmm, yeah, yes, okay. But why the name quotient? Like even in Z mod NZ, where is quotient? What is quotient? Something that we have been studying since we were kids is the quotient when we are dividing integers. So I'll tell what happened actually was that 27, say I have a number, say 27, and I'm dividing it by 3, I have a number 9. So this simply means that I can divide 27 into 9 groups and and this group is not the abstract algebra group, it's just simply groups, so maybe 9 sets. I don't know why my pen is not working. 9 sets, each having uh, each having number of elements 3, so each having 3 elements. Now can anybody think why it was called a quotient group? Not only that, I am in fact writing it as G mod n, somewhat like the division sign.
The number of equivalent classes formed is the quotient of the order.
Yeah, it's something like that. It's somewhat like grouping elements of a group, like forming sets of elements of a group. So what happened was that this is nothing but, so if you see all the cosets, all the left cosets have the same cardinality. Those sets will have the same cardinality. And how many number of cosets will I have? That will be nothing but the index, right? That is what I've defined index as. So G mod n is nothing but grouping into index number. So grouping into index number of sets, each of cardinality order of n. That is how the name quotients came about. And quotients are basically, they're somewhat like ignoring information which is not relevant. We are grouping stuff. So now we knew much more about the group when we knew each and every element, but now we know much less about the group when we have formed them into sets. So this is as a very normal example, I would say. I mean, it's not very mathematical, but if I have a clock which does not have labelings except for 12, and there is just one line over here and the hour hand, and I want to know what the time is, so I just need to know this angle alpha. I do not, so suppose this hour hand from the beginning, from the start, from when you have set up the clock, say it has moved about 360 n plus alpha till now, these many degrees. I do not need to know this 360 n. If I know alpha, I'm done. So this is somewhat what a quotient group is doing. It does not need to know everything about the group. So it is forming it into sets. So quotient groups are somewhat like not taking into account information which is relevant which is not relevant right now. So those are quotient groups. So I come back to my claim that the set of left cosets will form a normal group, will form a group if and only if, so if and only if that subgroup that we have taken is a normal subgroup. So G mod n is a quotient group if and only if n is normal. And n is normal means for all n in n, G in G, G and G inverse is in n. So G inverse NG or G and G inverse doesn't matter because both G and G inverse are in G. So we have proved one side, that if G mod n is a quotient group, then n is normal. So we need to prove the converse. The converse is if n is normal, then the set of left cosets G mod n forms a quotient group. So for this, we'll prove two things. One is G inverse is nothing but n if and only if n is normal for all G and G. And every left coset of n in G is also a right coset of n in G when n is normal. If we prove these two things, then we have proved our claim. So we prove one, we prove one, that G inverse is n if and only if n is normal. This is for all G in G. So G inverse is n implies that for all n in n, G inverse lies in n. And this is nothing but the definition of a normal group. Right? So one side is simple to see. This would imply that n is normal. Conversely, see G inverse, this will be a subset of n for all G and G. Is that fine?
Yes.
Yeah. So G and G inverse is a subset of N for all G and G. But there is nothing special about G. Why only G? I can take G inverse NG also. This is also a subset of N for all G in G. So N, but N is nothing but G, G inverse NG, G inverse. And this is a subset of G and G inverse because G inverse NG is a subset of N. But this is nothing but N. I mean, not even N from the previous, from this one, I'm saying that it is a subset of N. So this would imply that N is a subset of G and G inverse, which is a subset of N. So this would imply that G and G inverse is equal to N. So we are done. So we have proved 1, that G and G inverse is N if and only if N is normal. So we are left to prove 2. 2 stated that for if N is a normal subgroup, then all left cosets of N in G will be right cosets of N in G. So every left coset of N in G is going to be some right coset of N in G. So if N is normal, so for all G in G and N in N, I have Gn G inverse is equal to N from 1. This is from the first proof. This is nothing but Gn is equal to Ng. So I have proved that a left coset is going to be a right coset. Conversely, say every left coset of a subgroup in G is a right coset of a subgroup in G. So say I have a left coset Gn. So what should be the corresponding right coset? This is equal to some right coset. So can anybody tell me what should be the corresponding right coset?
The same NG because identity lies in N.
Yes. So the same Ng because identity is in N. So G should be in Gn and G should be in Ng also. G should be in Na, say. That A should be G. So the left coset Gn should be equal to the right coset Ng if the left coset is some right coset. But this is nothing but Gn. G inverse is equal to N. So this implies that N is normal. So we are done proving 2 also. That every left coset of a normal subgroup in G is also a right coset of a normal subgroup in G. So now we can go ahead with our converse that we wanted to prove that if N is normal, then G mod N is going to be a quotient group. So let N be normal. Then AN, BN, two left cosets of N in G, AN, BN in G mod N. So let me take AN, BN. This product, I need to prove that it also belongs to G mod N. But associativity holds. So this NB here is BN from the condition that N is normal. I have proved that every left coset is going to be a right coset. NB is going to be the left coset BN. So I can write this as ANBN is nothing but ABNN. This is nothing but ABNN. So NN is nothing but N only, which is ABN. And I've proved that the product of two left cosets is also going to be a left coset, which means closure holds, and it is not difficult to verify the other properties of the group. And this is going to prove that G mod N is a group. So we'll just go through it once. Say AN is some X and BN is some Y, then XY is going to be ABN. So x and y belong to G mod n, then xy belong to G mod n. This is what we have done till now. Now, let us prove associativity. Say x, y, and z are in G mod n. X is some an, y is some bn, and z is some cn. Here a, b, c are in G. Then x, y, z is nothing but an, b, and cn. From 1, this is nothing but an, b, cn, which is nothing but an, b, cn. Then I'll take this, I'll get a, b, c, n. Similarly, xyz is nothing but an, bn, cn. This is nothing but abn, cn. This is abn, cn, and this will be abcn. So I have proved associativity. Now I want to check an identity. An identity element, I'll say that let me consider n equal to en. This is also a left coset, right? Because E is an element in G. So this is going to be a left coset. So I'll take n equal to en. Now let x be some an in G mod n. Then nx is equal to an, which is equal to ean. And ea in the group is nothing but an, which is x. Similarly, xn is going to be an. This is going to be aen, and ae again is a. So an, which is x. So in G mod n is the identity element. So n is the identity. And finally, we need to prove that inverses exist. So suppose x is equal to an and y is equal to a inverse n. So if an exists, then a inverse n has to exist because a is an element in G. So a inverse will also be an element in G because G is a group. So if an exists, then a inverse definitely exists. So xy is nothing but an, a inverse n, which is a inverse n, which is en, which is n. So y is the inverse of x. So we have proved that it will be a group. Is that fine?
Yes.
Yeah.
Yeah.
So for some time now, we'll put aside this theory of normal groups and quotient groups, and we'll look at some examples of groups which are very important. And I'll begin with something called Abelian groups. I'm sure you've heard of the name. Does anybody know what Abelian groups are?
Commutative.
Yeah, they're commutative groups. So basically, it is saying that if G is a group and if A and B belong to G, then AB is nothing but B. So the operation that is being performed is actually the group operation. It's not multiplication. So if G would have been a group with addition, then A plus B is equal to B plus A, not A into B equal to B into A. So a very simple example of an abelian group is the set of polynomials over integers. So, and this group operation would be addition. So here the identity element would be the zero polynomial. And if a n x bar n plus dot 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 plus a naught is in zx, this implies that an, an minus 1, a naught, these all are in Z. So its inverse will be an minus an x bar n minus an minus 1 x bar n minus 1 minus a naught. And since an and an minus 1, a naught, all of these are in Z, then minus an minus 1 minus a naught, they are also in Z. Associativity is also easy to prove. So this is an example of an abelian group. So I'm going to talk about another example called the Klein 4 group. This group is actually used in music, and TED has a beautiful video on this group. So if anyone is interested, they can go and check ahead. The relation with music. And this group is denoted by V. So Klein 4 group, as the name states, we can just immediately tell that it is a group of 4 elements. It has 4 elements. So I'll say E, A, B, C. Since it is a group, identity element has to be there. So I'll say that it is E. And here, each element is the inverse of itself. That means A is equal to A inverse, B is equal to B inverse, C is equal to C inverse. Also, if I apply group operation on any two, if I perform the group operation on any two non-identity elements, I'll get the third non-identity element. That means AB is equal to C, BC is equal to A, and AC is equal to B. You can actually check that it is an abelian group. It's very easy, so I'll leave it to you. So what is special about this group? Sorry. So first thing, it is the smallest group to exist that is non-cyclic. So I think in the second session you guys had done cyclic groups, right?
Yes.
Yeah. So V is the smallest group that is not cyclic. So do you have any idea about Cali tables?
The very first lecture, there was a brief introduction.
Okay, so I'll just mention what Cali tables are. So Cali tables are basically, say I have a group with 2 elements. So I can form a Cali table over here. This is the group operation here. Whatever the group operation is, this is E, this is A, again E and A. So Cali table is going to write, if I perform group operation on E and E, what am I going to get? E. E and A, I'll get A. A and E, I'll get A. A and A, I should get E. This is why, because in Cali table, no column or no row can have 2 entries same. Why? Because suppose I have a Cali table, maybe say A, B, C, D, A, B, C, D, and say I have some X and X here. This is going to tell me that B, A is X and D performed with A is X. So this means B, A is TA. So A inverse, if I write multiply A inverse, then I'll get B is equal to T. But Cayley table is going to write all the distinct elements only, so B can't be equal to T. Similarly, for rows, you can do the same thing and you'll get a contradiction. So Cayley table states that no row or no column can have 2 elements same. So now if I have to construct the Cayley table for E, that is just a single group, single element group, then I have E over here. This is for 1. This actually tells me that up to isomorphism, there is only one group of order 1. Similarly, if I have to perform for groups of two elements, say E and A, then I know that this has to be E and A and E. So this has to be E. This can't be A. That means again, up to isomorphism, there is only one group of order 2. Again, for 3, if I have to check, for 3 elements, so E, A, B, E, A, B. Now, easily I can fill this. Suppose this A. Now, for this can have this column, this entry can either be E or be B, because I know it can't be A. So suppose I say that this is E, then this will be B, and I get a contradiction that one column has two same entries. So this can't be E. That means this has to be B, this has to be E, which means here in this column I have AB, so this has to be E. In this column I have BE, so this has to be A. So again, from Cayley's table, I'm actually proving that up to isomorphism, there is only one group of order 3. And this actually shows us that this group is going to be cyclic. Again, this group is going to be cyclic. The single group is anyways cyclic. There's nothing to talk about it. It's the trivial group. So what about 4? So groups of order 4. So maybe if someone can help me fill up the table. This I know. Yeah. So can someone just think about what the entry should be?
We can start with say one of them E.
Okay,
And
so suppose I put E over
then the next one has to be C and the next one has to be B, going by rows.
Yeah. Yes.
And going down from the second column again, that has to be C and the second one has to be B.
This one has to be B.
Yes.
Yeah.
And then this one could be A or could be anything, I think.
You're talking about this.
Yes.
It could be A or E. Yeah. Suppose it is E.
If this is E, then the one to the right is A, and the one below is A, and this is E again.
Yeah. Okay. So suppose so we got started with E. So we took E over here. What if I take A? Then this would have to be E. Then this would have to be E. And then this would have to be A. Right?
Yes.
Yeah. Okay. So if I go ahead, I can see that for groups of order 4, there is not just one group. There are multiple groups. But we are going to talk about this table over here. This is nothing but B, if you can see. Any element is the inverse of itself. That is why A is E. B square is E. C square is E. Again, if I perform the group operation on any two non-identity elements, I'm going to get the third non-identity element. So AB is C, AC is B, BA is C, BC is A, CA is B, and CB is A. So this is nothing but V. This table represents V. And if you see, this is not a cyclic group. That is, A square is already giving me E. Then how am I going to get the other elements, other non-identity elements? B square is again giving me E. C square is again giving me E. So how am I supposed to get a cyclic group? So V is actually, and from the Cali table I showed that the previous three groups of order 1, 2 and 3 were all cyclic. So V is going to be the smallest group which is not cyclic. So a question is it isomorphic to some group that we know? So you all can go ahead and try. There are only two groups of order 4 up to isomorphism. And one will be a cyclic one will be not cyclic one. So let me talk about one group which we all know, which is a cyclic group. Is it isomorphic to Z mod 4Z? This has 4 elements.
Here the basic property of the Klein 4 group is not satisfied.
What is the basic property?
That the inverse of the element is the element itself.
Yes. Okay. Yes, you're right. It is not isomorphic to Z mod 4Z. And on top of that, Z mod 4Z is a cyclic group. So it is not isomorphic to Z mod 4Z. That means it is isomorphic to some other group of order 4, and I will claim that it is isomorphic to Z2 cross Z2. This is nothing but Z mod 2Z cross Z mod 2Z. This is the Cartesian product. And this has these elements 0, 0, 1, 1, 0, and 1, 1. Is it easy to see that it is isomorphic to this? Can I find a mapping?
Yes, it's clear.
Yes.
Yes. So E will go to this. Then ABC are these 3 elements. Okay. Another way, so geometrically, this group is actually representing the symmetry group of rectangles. And by rectangles, it cannot be a square. It has to be a proper rectangle. So non-square rectangle. So it represents a symmetry group of non-square rectangles. So if I have to show that, suppose I have a rectangle, and this is 1, 2, 3, 4. I label them. Then I can flip it about this axis. Then I'll get 2, 3, 1, 4. Again, flipping it about this axis will give this back. So this flipping operation is the inverse of itself. Similarly, the same rectangle, I can flip it about this axis. It's again an axis of symmetry. So I'll get 1, 2, 3, 4. Again, flipping it about this axis will give this back. And if I compose these two operations, that is first I flip it about this axis and then about this axis, then I'll get 1, 2, 3, 4. I flip it about this axis. This is an intermediate step. I'll get 2, 3, 1, 4. Here I flip it about this axis. And so this is actually what is happening. And here I'll get 3, 4, 1, 2. So this is one element, this is 2 element, this is the 3rd element, and this is the 4th element. And this is the symmetry group of rectangles. So geometrically, V is representing the symmetry group of rectangles. Now I'm going to write something that so this is nothing, this whole thing is nothing but an element of something called a symmetric group. And this is what we are going to talk about next. We are done with Klein group, Klein 4 group. So we are going to talk about symmetric group next.
what does the empty bracket represent in the previous
Yes,
slide?
I will do that. Symmetric group. So symmetry in mathematics, symmetry is something that is invariant under some transformations. So transformations like translation, reflection, rotation, scaling. So the others are a bit easier to see. Scaling may be fractals. So fractals have scale symmetry. So even if you scale fractals, they look the same. So in mathematics, the symmetry is something that is invariant under some transformations. And so the symmetry group of a set is the bijection, is a set of bijections from that set to itself. So bijections are basically preserving the set structure. That is why symmetry or the symmetric group is a set of bijections. So if I have to write it down, let sigma be a non-empty set. Then S sigma is a set of all bijections. From sigma to sigma. So S sigma is F sigma such that F is a bijection. So the group operation is actually, this is somewhat how we are going to define it as a group. So this is from S sigma to S omega to S omega. Say some F and some G. So it maps to Fg. So we are actually interested when omega is 1 to n. Set of integers, set of natural numbers from 1 to n. And in this case, Sn is called the symmetric group of degree n. The symmetric group of degree n. So we call S omega nothing but Sn. And order of Sn is n factorial. I think this was done in the first session. This was introduced in the first session, right?
Yes.
Yeah. So since I am running out of time, I'll just quickly go through what Sn is. So suppose I have a sigma in Sn. Maybe I'll give an example in S8. So 1, 2, 3, 4, 5, 6, 7, 8. Performing sigma on this takes 1 to say 7, 2 to 5, 3 to 4, 4 to 3, 5 to 8, 6 to 1, 7 to 2, and 8 to 6. Suppose this sigma, which belongs to S8, takes 1, 2, 3, 4, 5, 6, 7, 8 to this set. So I am going to write this in a cyclic notation. That is, I will choose the smallest element that is in S8, that is 1. 1 goes to 7. Sigma takes 1 to 7. So I'll write 7 next. Then 7. Sigma takes 7 to 2. So I'll write 2. Sigma takes 2 to 5. So I'll write 5. 5 to 8. So 8. And 8 to 6. So 6. And 6 to 1. So again I have 1. Then again 1 will take to 7. 7 to 2. 2 to 5. So we'll close the bracket here. Now we'll take the smallest element which has not appeared in this bracket, and that will be 3. 3 goes to 4, 4 goes to 3, so I'll close the bracket over here. And this is nothing but how you represent sigma. This is a cyclic notation, the cyclic way of writing sigma. And this, if you go ahead and check, if you're always writing sigma in this form, these sets, these cycles will be disjoint. That is, they'll have no elements in common. In general, it is not true. In general, I can have sigma is equal to 1, 2, 2, 3, 1, 4. So if I have sigma something like this, then 1 goes to, so I'll start from here. 1 goes to 4, and 4 doesn't have any other appearance. So 1 goes to 4, then 2 goes to 3. Again, I do not have any other permutation. So 2 goes to 3, 3 goes to 2, 2 goes to 1. So 3 goes to 1, and 4 goes to 1, and 1 goes to 2. So 4 should go to 2. So sigma is basically taking 1 to 4, 2 to 3, 3 to 1, 4 to 2. So we can have such representations, but if we are using the algorithm, this algorithm to write down, so if I had that sigma takes 1 to 7, 2 to 5, 3 to 4, and I want to write sigma in a cyclic notation, then I will always get disjoint cycles. Is that fine?
Yes, it's fine.
Yeah. So this is the symmetric group, and the symmetric group is actually very important. It is used in a lot of areas, in representation theory, in Galois theory. It's used everywhere, and in fact, it is used to prove a very famous theorem in group theory called the Cayley's theorem. The Cayley's theorem, so I'll just state the Cayley's theorem. It says that every finite group is isomorphic to a subgroup of Sn for some n. That means it just simply says that if I study Sn, the symmetric group, and its subgroups, then I have studied every finite group. So Sn is actually very important. Now we move to something called alternating groups. So alternating groups, right? And also, someone had asked, what is this empty bracket indicating? This is nothing but the identity. So this is taking 1 to 1. This, so if sigma is this, then it is taking 1 to 1, 2 to 2, and so on. So now we move on to something called alternating groups. Alternating groups are so if I have an alternating group AN, it is a subgroup of Sn which has index 2. Exercise, maybe all of you can try, that any subgroup which has index 2 is a normal subgroup. You can just think about it and you'll get the answer. So any subgroup which has index 2 is a normal subgroup of the group. Now, alternating groups are basically the group of all even permutations in Sn. And so there is something called sign in. So I do not know if I have time to explain that, but I'll just quickly go through it. So every sigma, no matter how it is, 1, 2, 3, and then 4, 5, 6, however sigma it is, I can write it as a product of two cycles. Two cycles are basically cycles which have two elements. I can write it as a product of two cycles. So just as an example, if I have a cycle, say 1, 2, 3, 4, 5, 6, this sigma is basically taking 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on. I can write it as 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. So if you see, 1 goes to 2, 2 goes to 1, here 1 goes to 3, so 2 goes to 3. 3 goes to 1, 1 goes to 4, so 3 goes to 4. 4 goes to 1, 1 goes to 5, and you only move in the left direction. It's composition happening over here. So 4 goes to 1, 1 goes to 5, so 4 goes to 5, and 5 goes to 1, 1 goes to 6, so 5 goes to 6, and 6 goes to 1. So we can actually prove that every permutation, every sigma can be written as a product of two cycles, and two cycles are known as transpositions. So is that fine?
Yes.
Yes.
Yeah. So there is, so I'll make a claim. I won't be proving this, but you can look up the proof, or I can share the notes if you want after this session. So I'll claim that if sigma can be written in infinitely many ways if it is not disjoint, if the cycles are not disjoint. So here these cycles were not disjoint. One was there. So if it is disjoint, it can be uniquely written. There is another proof for it. But if it is not disjoint, if these cycles are not disjoint, then sigma can be written in infinitely many ways. So sigma as a product of two cycles. So if I say that I have a sigma which I can write as a product of even number of two cycles. Then any other way of writing sigma as a product of two cycles will have even number of terms. That is, the number of two cycles will be even. So if one way of writing sigma as a product of two cycles contains even number of terms, then any other way of writing sigma as a product of transpositions or two cycles will contain even number of terms. Similarly, if I can write sigma as a product of two cycles which contain odd number of terms, then any other way of writing sigma as a product of two cycles will contain odd number of terms. And there is a proof for it. And maybe I can share the notes with you after this session so you can go through the proof ones. So, and so now I'm going to talk about the sign. And let us talk about something called delta. Delta is nothing but product of xi minus xj, where 1 less than I less than strictly less than j less than n. And I'm going to talk about sigma as a product of transpositions, as a product of two cycles. Say, so suppose sigma is 1, 2, 3, 4, 5. Then sigma of delta is nothing but product of x sigma I minus x sigma j, where 1 is less than I less than j. So I'll give a simple example. Say I have 1, 2, 3, 4, 5, as I had said, sigma is this. So my sigma of delta is going to be, so I'll start with I as 1. So when I is 1, sigma of I is 2. So x2 minus, now j has to be greater than I, so maybe 2. So when j is 2, this will be x1. Then when j is 3, it will be x4. When j is 4, it will be x5. When j is 5, it will be x3. Then if I is 2, then I'm going to get sigma I as x1. So it will be x1 minus, now when j is 3, it will be x4. When j is 4, I'll get x1 minus x5. Then I'll take I as 3, so I'll get x4 And when j is 4, it will be x5. And yeah, right, sorry, here it will be x3 also. And here I'll get x4 minus x3 for j equal to 5. Then I have I equal to 4. I'll get x5 minus x3. Is that fine? Or should I just repeat this once more?
It's fine, I think.
Okay. So
Sorry for
now,
how are you getting
yeah,
the I and J's?
I is just from 1 to n and j is greater than I here.
Okay.
Yeah. So, and delta for this, delta actually for 5, for n equal to 5, I'll get x1 minus x2, x1 minus x3, x1 minus x4, then x2 minus x3, x2 minus x4, x2 minus x5, sorry, x1 minus x5, then x3 minus x4, x3 minus x5, and x4 minus x5. So so if you actually go ahead and check, sigma delta and delta can only differ by a sign. Either they are going to be equal or they are going to be negative of each other. So you can just check this, it is routine. So I'm going to define something called epsilon of sigma, which is 1 if sigma delta is delta, and minus 1 if sigma delta is minus delta. And this is the sign of sigma. So if epsilon of sigma, that is sign of sigma, is 1, that is sigma delta is equal to delta, we call it an even permutation. And if it is minus 1, then we call it an odd permutation. And an is just the set of all even permutations of Sn. That is known as the alternating group. Then we have something called the dihedral groups. And the dihedral groups are basically talking about, so a rigid motion. So I'll first talk about something called a rigid motion. A rigid motion is a map. It is a distance preserving map. So suppose M from R2 to R2 is a map. It is a rigid motion if the distance between x and y in R2 is the same as the distance between mx and my. This is called a rigid motion. So if a rigid motion carries a subset to itself, it is called a symmetry. This is basically what I was even talking about before defining symmetric groups, is that a symmetry is something which preserves, which in the set of sets, it preserves the set structure, but in general symmetry, something which remains invariant under transformation. So here the distance is remaining invariant under this map. It remains invariant under this transformation. So for a dihedral group, it is basically if I have a pentagon, or maybe let me take a simpler example. Maybe if I have a square, which I have labeled. Now this I claim that I can perform 8 operations on this. Rotation 4 times. So if I rotate once, I'll get 1, 2, 3, 4. If I rotate twice, I'll get 1, 2, 3, 4. If I rotate thrice, I'll get 1, 2, 3, 4. And if I rotate once more, I am getting the same 1, 2, 3, 4 back again. So there are 4 operations like this, 4 for different structures, I'll get like this, and I can flip it about these axes. So D2n, it is also like some people do denote it by Dn. Dn here actually represents the vertices of the polygon that you have chosen, and D2n will represent the number of elements in this group in D2n, the order of D2n. So I am denoting it by D2n. So D2n is nothing but, in this case, it will be D8. And it will be all the possible operations that I can perform on this polygon. It needn't be a square, it needn't be a rectangle, it can be um, pentagon, decagon, nonagon, it can be anything. And accordingly, we do find D2n. So there will be n rotations about the center and n flips. Okay, I won't go into detail because we are running out of time. And I'll just introduce something called matrix groups. So I'll introduce something called matrix groups. So have you all heard about GLNR? Does anybody have an idea of what is GLNR?
Yeah, it was discussed last lecture.
All the matrix groups have been discussed?
No, GLN and SLN.
Okay. Okay, then since I am running out of time, I won't go into like the other matrix groups such as ON and UN. I'll just talk about the isomorphism theorems. So first, let me talk about homomorphism. I think in the first session, this was introduced, homomorphism. So homomorphism phi from a group G to a group H. So this is nothing but, it says, so a homomorphism says that phi of A dot B is phi A dot phi B. It should satisfy this condition. So here, if you notice, I have put star over here and dot over here. This is because star is the binary operation on G and dot is a binary operation for H. So it isn't necessary that the operation over here should be the same operation over here. So it is a map from G to H, satisfying the condition that if A and B are in G here, for all A, B in G, if A and B are in G, phi of A into B is equal to phi of A, phi of B. Is that fine?
Yes.
Yeah. So next, image of phi. Image of phi is all x in H such that x is equal to phi of A for some A in G, for some A in G. And we define something called the kernel of phi. Kernel of phi are all A in G such that phi of A is the identity element of H. Is that fine?
Yes.
Right. So now we talk about something called the isomorphism theorems. And there are actually 4 isomorphism theorems, and I will only talk about one of the isomorphism theorems. And isomorphism theorems are actually very important. They are used to prove a large set of things in group theory. Not only group theory, you will go ahead and have isomorphism theorems in rings, fields, modules. Everywhere you will be using the isomorphism theorems. So we are going to talk about only the first isomorphism theorem, which is the most widely used isomorphism theorem. And if you go ahead and read in some books, actually the isomorphism theorems, they will state only the first one, and they usually give the remaining ones as an exercise. I think in R10 it is given like that. In Tomato Input, maybe we do get uh, all the isomorphism theorem. So I'm going to talk about the first isomorphism theorem. So if phi from G to H is a homomorphism, then kernel of phi is a normal subgroup of G. Kernel of phi is a subgroup of G, so it's a normal subgroup of G, and G mod curl phi is isomorphic to the image of phi. So, anyone has any problem with the notations? Do they want me to explain G mod curl phi? What is this symbol?
I think it's okay.
Yeah, okay. So, proving this theorem is actually quite simple. So let us take phi from G to H. This is an isomorphism. This is a homomorphism. Let kernel of phi, we denote kernel of phi as K. So K, first claim was that K is a normal subgroup of J. So
If that is, if say small k belongs to capital K, and let G be any element in capital G, then G inverse Kg is always this will also map to the identity element. So this is also an element of K.
yes, you are right. Maybe you can give mention it in terms of phi.
Then phi of G inverse Kg will be equal to phi of G inverse phi of K phi of G. But phi of K is 1, so it's phi of G inverse into phi of G, which is 1.
Again 1.
I mean, E.
Yes, you're right. Thank you. So, basically, what it was that if K is in K, then phi of K is EH, that is from the definition of the kernel. So phi of G inverse Kg for all G in G, this is nothing but from the definition of the homomorphism, this is phi G inverse, phi K, phi G. This is EH. So this is nothing but phi of G inverse G, which is phi of EG. And a homomorphism maps the identity element of G to H, the identity element of H. So it will be EH. So this is simply implying that G inverse Kg is of G. So we are left to prove that G mod K is isomorphic to the image of phi. So let us take maybe capital phi from G mod K to image of phi. We had phi as G to H, which is a homomorphism, and K. So to check that this is a homomorphism, this phi, this capital phi is a homomorphism, let me take G1K and G2K in G mod K. So first we prove that it is a homomorphism, then we go ahead to prove that it is bijective. So phi, capital phi of G1K, I don't know, something is wrong with this pen, and G2K is equal to phi of G1, G2K, because I have proved that K is normal, right? And this is nothing but phi of G1, G2, small phi. This was capital phi. This is phi of G1, G2. And this is nothing but phi of G1, phi of G2, which is capital phi of G1K, capital phi of G2K. Is there any problem in this?
No.
Okay. So I have proved that it is a homomorphism. So all that remains is to prove that it is bijective. So so if I want to say that it is 1, 1, so let me consider that phi of G1K is equal to phi of G2K. Then I need to prove that G1K equal to G2K for it to be 1, 1. So this implies that phi of G1 is equal to phi of G2. This implies phi of is equal to E. This implies phi of G1 can prove using homomorphism, so you can go ahead and try to prove this. So phi of G1 inverse phi of G2 is E. This implies phi of G1 inverse G2 implies G1 inverse G2 belongs to the kernel of phi, which is nothing but K. So this implies that G1K is equal to G2K. Is that fine?
Yeah.
Yeah. So we are done with proving 1, 1. Now, phi, this capital phi is onto. Is there any problem with that? It is very clear why it is onto. So can anybody tell me why it is clear that it is onto?
Since K is normal, every element in image of phi belongs to one of these equivalence classes.
Yeah, since we are taking image of phi and not H.
Yes, yes, yes.
Yeah, so that is why it is onto. So this proves that this is going to be a bijective. So phi is a bijective homomorphism. But bijective homomorphism is just an isomorphism. So we prove the first isomorphism theorem that that if phi from G to H is a homomorphism, then kernel of phi is a normal subgroup of G, and G mod kernel of phi is isomorphic to image of phi. So does anybody want me to go through any of these concepts that we have done till now? If not, then maybe I can give you an example of symmetric groups. All of you can maybe try this. Say sigma is okay. Maybe I'll talk about this one thing that I left out. That sigma say sigma is 1, 2, 3, 4. And I say sigma belongs to Sx. Can anybody tell me what X is?
S4? I mean, X is 4?
It can be
Yeah,
any n greater than equals to 4.
yes, it can be any n greater than equal to 4 because if it if it was S5, then it simply means that 5, this element 5 is sigma is mapping 5 to 5. So it can be any element. So X can be any number greater than equal to 4. That's right. So before I stop, actually, I was going to talk a bit about symmetric groups, uh, which you know they we can see them in a lot of places. They are symmetry. We call them symmetry. So where do we see symmetry? We see patterns all around us, right? So basically, repetitive patterns are used all around us, especially in maybe walls, the wallpapers in our rooms. If we apply some wallpapers, there is a repetitive pattern going around. So this actually has a group in mathematics called the wallpaper group, and it is a group of isometries. And isometries are again digit maps. They preserve the distance. So intuitively, when we are talking about something called repetitive patterns, we think that there are infinitely many wallpapers, that I can find infinitely many wallpapers with repetitive patterns. And it's quite obvious even in the real world when we go around looking at different wallpapers, we see there are so many kinds of wallpapers. But actually, uh, a Russian mathematician, in fact, proved that there are only 17 possible patterns. That is the wallpaper group. There are only 17 wallpaper groups. So any pattern that you see, uh, any patterns that you come across, it belongs to one of these groups, one of these 17 groups. And symmetry groups actually help us understand these geometric restrictions to create these patterns. And there is a very huge, deep underlying theory behind it, which I won't go into. But this is something which I found really cool when I was studying groups, that there are only 17 patterns, and any kind of pattern that I'll see is going to belong to one of these groups. So maybe actually I might have those pictures. Um, Maybe let me check if I have those 17. Yeah. So, in fact, these 17 patterns, these seven, so any pattern that you see, it belongs to actually only one of these. So, I'll end with this note. It's somewhere thing about symmetric groups, but yeah. So that's all that I had to talk about. I know I rushed isomorphism theorem a bit, but we were already running out of time. So I will share the notes, if possible, of the remaining 3 isomorphism theorems. In fact, all of you can go ahead and try to prove those isomorphism theorems, the second, third, and fourth isomorphism. So thank you.
Thanks,
Thank you,
Didi.
Pratichi. Uh, this was a
Thank
great
you.
talk.
Yeah, if there is any question, you can ask, or in fact, you can mail me also. If there are no questions, Rahil, can we stop?
Yeah, I'm not the host. Venkat is the host. So, Venkat, please end the meeting and have a nice weekend, guys.
Okay. Thank you.